Welcome to my presentation on entropy, enthalpy, and Gibbs free energy. Thermochemistry is a branch of chemistry that focuses on heat energies associated with chemical reactions. So heat energy is transferred between a system and its surroundings as a result of the temperature differences. The collisions, energy passes from a warmer body to a colder body by molecules hitting each other. An exothermic reaction is one that produces a temperature increase in an isolated system. It gives off heat to its surroundings, and the heat of a reaction is negative. An endothermic reaction is when the temperature decreases in an isolated system. It then gains heat from its surroundings, and the reaction is positive. So enthalpy is a state function in which H is the sum of the internal energy and the pressure volume product. So in this equation here, delta H equals delta U plus P delta V, where delta H is the enthalpy, delta U is the internal energy, and the PV is the pressure volume product. At constant pressure, the heat evolved is equal to the change in enthalpy. The modern interpretation of entropy is firmly rooted in the idea that microscopic systems is made of tiny particles. And because those particles are in continuous random motions and experience collisions with each other in the walls of the container, the positions, velocities, and energies of individual molecules change from one instant to the next, meaning there are very much many possible microscopic configurations, also known as microstate. A microstate is characterized by specifying the quantum state, which is the quantum numbers and energy of every particle. So entropy is a thermodynamics property that is related to the way in which the energy of a system is distributed among the available energy levels. So this guy here, Ludwig Boltzmann, associated the number of energy levels of the system with the number of ways of arranging the particles. So in this equation, delta S equals KB ln of W, where KB is the Boltzmann constant and W is the number of microstates, and delta S is the entropy. So there are four different situations in which entropy increases. So the first one is when liquids are formed from solids. The second one is when gases can be formed from liquids and solids. The number of molecules of a gas increases in a reaction, or the temperature of a substance increases. And as a common rule to relate entropy and spontaneity, if delta S is greater than 0, then the process is spontaneous. If delta S is less than 0, the process is non-spontaneous. And then if the delta S is equal to 0, the process is reversible. So let's explore a hypothetical process called the Gibbs free energy that occurs at constant temperature and constant pressure. So Gibbs free energy is defined by this equation, delta G equals delta H, which is the enthalpy, minus T, which is the temperature, times delta S, which is the entropy. So if delta G is negative, the process is spontaneous. If delta G is positive, we know the process is non-spontaneous. And if delta G equals 0, the process is reversible and the system has reached equilibrium. So the standard Gibbs energy of reaction is defined as the Gibbs energy change per mole of reaction. And say, for example, we have an equation like this where A plus B equals C plus D, and then the delta RG is the products minus the reactants, and it's the Gibbs free energy values of that. We can find those Gibbs free energy values, those standard Gibbs free energy values in a table in the textbook. And if we look on the table here, we see some rules that we can use in everyday equations. So for example, if delta H is negative and delta S is positive, delta G will therefore be negative and it will be spontaneous at all temperatures. But say, for example, delta H is positive, delta S is positive as well, and then delta G could either be positive or negative, and depending on that, it can be non-spontaneous at low temps or spontaneous at high temps. It all depends on what the delta S, delta H, and delta G are. So the equation we just saw was for Gibbs energy in standard conditions, but what happens when Gibbs energy is in non-standard conditions? We would then use a different equation, which is shown below as delta RG equals delta RG of the standard conditions plus RT ln of Q, where Q is the reaction quotient. Q can be defined as the partial pressure products over the standard condition divided by the partial pressure of reactants over standard conditions for gases. For liquids and solids, the activity is always 1, and for solids in an aqueous solution, the ideal solution behavior assumed for the activity is replaced by molarity. Bioenergetics is another example of a real-world application because the oxidation of glucose to carbon dioxide in water is accompanied by a large negative free energy change. The breakdown of glucose is a series of steps in which the energy is liberated at each stage and will be captured by energy carrier molecule, also known as ADP. At each step, ADP molecules react with inorganic phosphate and changes to ATP. Free energy is released when the molecule travels to a site where it is needed and loses one of its phosphate groups.
For our first question, at 298 Kelvin for the given reaction with a standard molar enthalpy of negative 620.2 kilojoules per mole and the standard molar entropies as shown, determine the Gibbs free energy at 298 K and whether the reaction proceeds spontaneously in the forward or the reverse direction when the reactants and products are in their standard states. So first, when we're looking at this equation, we notice that PCl3 and POCl3 has a 2 in front of each. So when we're putting that into our equation of standard molar entropies, we want to make sure we put a 2 in front of each. So when we're inputting our values from the given molar entropies from the equation, also which you can find in the appendix D of the textbook, we can input our values and get 222.4 minus 2 times 311.7 minus 205.1. And then if we put that in a calculator, we would get negative 383.7 joules per Kelvin mole. And then using this value that we found, and then the molar enthalpy given in the equation, we can use that to find the Gibbs free energy. So inputting our values, we get negative 620.2. We want to make sure this is in joules, so it's times 10 to the 3 joules per mole minus the 298 Kelvin. Minus the value we just found, 0.7 joules per mole. And then putting that into our calculator, we would get negative 506 times 10 to the power 3, but we'll just change that to negative 506 kilojoules rather than joules per mole. And so if we want to know whether the reaction proceeds spontaneously in the forward or reverse direction, it will proceed spontaneously in the forward direction because delta RG is less than 0. A possible reaction for converting methanol to ethanol is shown in this equation below. In A, use appendix D in the textbooks to find delta H, delta S, and delta G at 25 degrees Celsius. Is this reaction thermodynamically favored at high or low temps or at high or low pressures? And then estimate K for the reaction at 750 K. So because A is very similar to the example we did above, as we use kind of the same values from the table and the same equations, taking the liberty of already filling it out to save time. So here you can see all the values, though I do encourage you to do it yourself. And so for B, we want to know whether this is favored at high or low temps or high or low pressures. Looking at our delta RH, we can see that delta RH is negative or less than 0, meaning this is favored at low temps. And then if we look at how many gases there are, how many moles of gas there are on each side, we see that this side has 2 and this side has 4, meaning therefore positive 2 minus 4 equals negative 2. Therefore, the reaction is favored at high pressures. Moving on to C, I've taken the liberty of also inputting the values into the equation, which is delta H minus T delta S, and it would have been the same equation here, just at a different temperature. As here, you can see it's 298K, and here it's 750K. So inputting this value into our calculator, we would get 4.9 kilojoules per mole. And then because we want to do this at non-standard conditions, this delta RG is then equal to negative RT ln of K. So we make those two equal each other. And so to find what K is, we want to divide out RT. So we do this by going like this, positive, my apologies, 4.9. Let's make this joules now. So we want to do 10 to the power of 3 joules per mole over RT, which is the Boltzmann constant, 8.3145 joules per mole K, and then T, which is 750K, which was given in the example. From there, we would get the value of negative 0.79, and then we're left with ln of K. And so to find K, we put E equals negative 0.79. Inputting that into our calculator, we get 0.5. And that is our K value.
Thank you all for watching.